Well, good afternoon, everyone. I'm going to be your moderator this afternoon, and thanks a lot for logging into this webinar session. First things first, on the right side and at the bottom of your screen, you have a chat. That's the way to communicate with us. So please feel free at any time to drop a question through the chat, and I will take note of it, and at the end of the presentation, we will do a Q&A with Brian. So I will start by introducing Brian. Brian Crater is going to be our speaker this afternoon. Brian is Fermentis Regional Sales Manager, and he covers Central North America. So I'm going to start with a short bio of Brian. He started his working career in conservation, and around 2004, he began homebrewing with colleagues. And through the time, he became more and more involved with the hobby. In 2013, he had the opportunity to complete the CBL Institute short course in brewing technology and began working as an assistant brewer with a startup brewpub in Wisconsin. After about 6 months, he assumed the role of brewmaster for the brewery for the next 4 years and helped expand the brewery into distribution throughout Wisconsin. Brian, as I mentioned before, has been working as a regional sales manager for Fermentis, covering Central North America since March 2019. So thank you, Brian, and now the floor is yours.
All right, thanks a lot. Well, again, welcome everyone. Thank you for joining us here today. I'm going to go ahead and get started. So the presentation today is you can break it up into 3 different sections. The first section would be the production and drying process. And I'll go over kind of a general overview of the manufacturing process, talk a little bit about propagation, some specifics on drying, Fermentis quality procedures, discuss our microbiological specifications, and then also talk about some of the advantages of active dry yeast. Sorry, go ahead. I thought I just heard somebody talking there. So the second section would be our shelf life study. So in this study, it's kind of what we've done to establish our best before use date on our package. So we'll discuss our forced aging tests, natural aging tests, and then the conclusions from that study. And then the third section is where we'll talk about some of the most frequently asked questions we get revolving around rehydration procedures, direct pitching, and what ideal conditions for rehydration, and then discuss direct pitching's impact on yeast cell viability, vitality, and then discuss the conclusions. Okay, so production and drying process. So here's a diagram of kind of the overall manufacturing process. And there are 4 main phases to the process. The first is, I'm going to grab my arrow laser pointer here. The first is the laboratory phase. And then we move into the industrial propagation. And then the third phase would be separation and drying phase, and then finally packaging. So the process starts, every time we go to produce a new batch of a strain, we start at the laboratory with a culture that has been cryogenically stored at -80 C. And that culture in the lab is grown in a small flask, producing just a few grams of yeast, and then eventually a larger flask producing a few 100 grams of yeast. In this laboratory phase, this is all entirely sterile process. This is very similar to what you might do at home, making a yeast starter if you're using liquid culture, or if you have some yeast of questionable viability, you might do a starter like this to step up the cell counts. But once the laboratory phase is complete, then we move into the industrial phase in a series of sequentially larger vessels. In the pre-fermentation vessel, we produce a few hundred grams or a few hundred kilos of yeast. And then in the larger propagation vessels, producing a few tons or even a few tens of tons in our largest vessels. This process is fully aerobic, and it's important for it to be fully aerobic. So to do this, we need a carbohydrate source, which is sugar. We also need a large amount of oxygen that we feed to the tanks in huge volumes. We have massive turbines for this purpose that feed about, I think it's around 10,000 cubic meters of sterile air to the tanks per hour, which is pretty incredible. They're some of the largest turbines in the industry. But we're also, so it's a fed batch propagation. So we're continually monitoring and feeding the sugars, the oxygen, nutrients, vitamins, and trace elements into the vessel, providing the yeast growth factors it needs to grow. So following the propagation, we move into separation. So first in a centrifuge, removing the bulk of the water or the bulk of the growth medium. And then the yeast moves into cream yeast storage. Cream yeast storage is at around 4 degrees Celsius. And then following this phase, you can kind of go 2 different directions. So Lasoff Group services many different industries. So we can move from cream yeast storage directly into packages, whether they're bladders or totes or trucks, and ship them to customers. All Fermentis yeasts are in dry form, but it's just kind of important to know that if we wanted to produce liquid yeast, we could certainly do that. But we choose to offer only dry. So for the Fermentis brewing yeast, the next phase would be the rotary drum vacuum filter. So the yeast slurry is introduced onto the surface of this rotating drum that has a permeable membrane, and there's a vacuum applied to the inside of the drum that pulls water out of the yeast, which is then scraped off the external surface of the drum. And then this, at this point, it would be around 30-35% dry matter, and then is fed to an extruder where it's pressed out into, it's almost like a Play-Doh extruder. It makes like a yeast spaghetti coming out of the end. And then this yeast spaghetti is fed into a large drying plant called a fluidized bed air dryer. And what that means is warm air is fed through a bed of yeast, and that warm air has a higher capacity or very high capacity for holding moisture. So that warm, dry air passing over the yeast pulls moisture out of the yeast without increasing the actual cell temperatures to the point where it would damage the yeast or decrease viability in any way. And then following that drying step, we then go into the package. So this is a diagram showing what's happening inside of the propagating tanks. This is the cell division cycle. Again, our goal is to produce biomass. So basically every time we complete this cycle, we're doubling the amount of yeast, producing genetically identical daughter cells. One of the important things to ensure that we have very high viability yeast in the end is to be able to stop this process at the right time before we move to the drying phase. So the goal is to stop this division when the highest proportion of cells are in the whole form and not in the middle of budding. If we were to proceed with drying with a lot of cells in the budding phase, it can actually damage the cell walls and then affect viability and vitality. Each strain has a different amount of time that it typically takes for division. So that's one of the ways that we can know when it's appropriate to stop, but we can also somewhat control this process by controlling the inputs to the tank. I mentioned earlier that this is a fully aerobic process, and that's important because in a fully aerobic fermentation, so I should have mentioned earlier that the sugar concentration that we're introducing into the tank, we ensure that we keep that below 0.5% alcohol or 0.5% sugar. And what that accomplishes is we avoid the Crabtree effect so that no alcohol is actually produced in the process. But in this fully aerobic condition, we ensure that the yeast are fully saturated with unsaturated fatty acids and sterols in the cell wall. So an aerobic fermentation is actually, it's able to produce, the yeast are able to produce considerably more unsaturated fatty acids and sterols than in a typical brewery propagation. So because of that, once we've dried our yeast, there's no actual need for oxygenation on the first generation. So that's, if any of you have ever heard us communicate that, that's one of the reasons that we say that. But once we've gone through this process and dried the yeast, the cell walls are ready, the doors are open for sugar assimilation, and ready to go out of the package. Okay, so here's some microscopic images of yeast before and also after drying. So here on the left, you see nice round plump yeast cells. They kind of look like grapes. On the end here, you can see a budding scar, but the surface of the cell is smooth. And in this photo, this yeast would be at about 25 to 30% dry matter. After drying, you can see that the cell walls are more irregular. They kind of look more like a raisin. The cell wall is very uneven surface, so it's kind of folded in on itself. And after drying at this phase, we're at about 94 to 96.5% dry matter. And at this level of dryness, there is no free water left within the cell. And one of the reasons this is important, one is that it limits any potential microbial growth, but also it allows you to be able to freeze the yeast. So any remaining water is actually bound within molecules. So when the yeast is frozen, there's no crystals formed that would damage the cells. Okay, so here's an overview of our quality procedure, all the way from when we obtain a new strain through to the factory. And then on the next slide, we'll see the process through the factory. But we come about new strains of yeast in a few different ways. One might be that the yeast was isolated from the wild. It might be purchased from another yeast bank, or a customer may bring us a strain that they would like us to toll manufacture for them. So once we receive a yeast, we do an array of tests for genetics, purity, properties, and those are documented before the culture moves into our main yeast collection. And this is the La Sauf R&D yeast collection. And this is basically every yeast strain that we have within the company. And then any strain, not necessarily, or very few of these actually make it into a product that's in the market. But if a strain if we desire to take a strain to market, we again take that culture, check the genetics, purity, and properties, validate it against what the original culture is supposed to be, conduct a propagation, and then that moves into our industrial yeast collection. And this collection is everything that we have that's commercially available, or that we think we might like to make commercially available. And then from this collection, we again, every time we're going to produce a new batch of any strain, we take the culture from this collection, again, check genetics, purity, and property against the original parent culture, do a laboratory propagation to produce the daughter line yeast tubes, and then again check genetics and properties before that yeast tube is sent to any one of our factories. And we have several, kind of our main factories in Belgium, but we also have some other factories in other parts of the world that we use. Okay, so continuing on, we have the daughter line yeast tubes being received into the laboratory at the plant, where they again conduct a laboratory propagation, do all the purity controls, move into the industrial phase where we're producing the biomass, drying, and also packaging. And then we move into storage before our final analysis. So at this point, again, we check all the purity, viability, composition, check all the same things again, but also some additional tests for contaminants. We do aging tests. Many of the strains go through attenuation tests, plating for various contaminants, etc. And every lot of yeast that we produce must meet all of our criteria and have a positive quality release before it's released to customers. Rather than send the product to market and discover there's an issue and try to conduct a recall, we try to prevent that product from ever reaching the market in the first place. So here we're going to discuss our quality specifications. So this is actually for ales here on the left. But we do get some questions on this about how many viable yeast cells are actually in the package. And when you receive a technical data sheet from us or look at our website at the information, our ale strains are stated to contain 10 billion CFU per gram. But what this number means is this is the minimum cells in the package at the end of the 3-year shelf life when stored at ambient temperature. So, if you've had a product around for 3 years, this is what we're guaranteeing at the end of that time frame. So in reality, at the moment it's packaged, it's going to be slightly higher than this, but we need to create a statement that is uniform throughout the life of the product. So the next thing I'll talk about is different contaminants. So first is lactic acid bacteria. And we have some of the tightest specifications in the industry on this. We guarantee less than 1,000 colony-forming units per gram of yeast. For lactic acid bacteria, acetic bacteria, pediococcus, and then total bacteria less than 5,000 colony-forming units per gram. So if this seems like a big jump, but if all the other bacteria that we look at were at maximum, this would be the maximum allowed per gram. But why is this important? Well, these are actually very low levels. There is no such thing in biology as a pure culture. At these low levels, there's basically, when you have isoalpha acids in your wort, and also shortly after fermentation starts, you have alcohol. There's really no potential for growth of these bacteria at these levels. Then we look at wild yeast is also less than 1,000 colony forming units per gram. And again, this is less than 1,000 cells per 10 billion yeast cells. So there's really no way for that level of contamination to compete. That's perfectly okay for fermentation. I would say that these specifications that we have today are substantially better than the mid to late 90s when dry yeast was beginning to be used for brewing. Back then we recommended that, or it was understood that dry yeast was for one-way usage. But with our tighter specification these days, we're comfortable recommending up to 6 generations of use or 5 repitchings. And this is somewhat dependent on the yeast strain. But so you might, in your own brewery, you might be able to achieve slightly different results. Some strains you might be able to go a little bit longer than that. But that's things that you can work out in your brewery. So I see a comment. I can turn my camera back on if you really want. So we're going to look at what this would mean once you're actually pitching this yeast into the beer. So on the left, we have the same values expressed in a slightly different way. And then we look at pitching an ale at a rate of 50 grams per hectoliter, or approximately 60 grams per barrel, and what this translates into. So the number of viable cells would be, at this 50 gram per hectoliter pitching rate, would be 5 million cells per milliliter. And then you would have less than 1 lactic acid, acetic, or pedibacteria per milliliter. And this calculates out to a purity of higher than 99.999%, which is extremely pure. So less than 1 lactic acid bacteria per 10 million viable yeast cells. And for lagers, it's very, very similar numbers. Okay, now I'm going to talk about the advantages of dry yeast. We get the question a lot, or a lot of times people will ask us, which is better, liquid versus dry? And I don't think that's really the right perspective to have. They both have history of being proven to produce consistent results in the brewery. However, active dry yeast has some really specific advantages over liquid. The first is the flexibility that it offers. Managing multiple strains in a brewery can be really complex, and it's a really easy way. Dry yeast is an easy way to increase the genetic diversity of your brewery. But also, if you're, say, a large regional brewery, or you're contract brewing, or you just have 6 brew pubs that you're producing at, it can really facilitate those types of operations by not needing to maintain cultures at all of those sites. You can, because of its shelf stability, you can just keep the strains you need in stock at each of those sites, or easily ship them out. Another thing is that it can really facilitate experimentation, or seasonal products. So say you've got a facility where you're propagating, or you have a house strain that you consistently manage, but you want to bring something in for a one-off or a seasonal release. I know that when I was doing those things, often I wasn't really sure when I would get around to doing the experimental brew. So sometimes those were difficult to plan into the production schedule. But with dry yeast, you can have that brought in and keep it on the shelf and use it when the time's right. Dry yeast is, very consistent and reliable. You know that every time you receive a package that the composition, the genetics, the quality are all the same every single time. 10 grams of dry yeast today is the same as 10 grams tomorrow. So. You can also very accurately, because of the consistency of the product, accurately convert that dry matter weight into a yeast cell count. So because dry yeast is a dry ingredient, we do recommend all of our pitching rates as a weight per volume, because it needs to be treated as a dry ingredient. So dry yeast is very easy to source. Because it's so dry, it's 94 to 96% dry matter. There's a very low weight to volume ratio, which means that it's less costly to ship. There's no need for refrigerated transportation. So no need for ice packs or special packaging or overnight shipping or anything like that. So, and we'll discuss a little bit more about that later. Very short lead time, or distributors are typically very well stocked and get you yeast in short time. So, okay, easy to store. You will see a little bit later, there's a lot of flexibility in storage temperatures. It can be frozen. You can store it in a refrigerator, and for short periods of time, it's okay to store it at ambient temperature. With a 3-year shelf life, if you brought in a strain and you didn't have a chance to get to use it, you can put that off for another time, and that's not sitting there deteriorating rapidly on your shelf. Whereas a liquid culture in a couple months, 2 to 3 months, it's probably not okay to use, or you would have to do some kind of starter. Another point here with easy to store is it's easy to keep kind of a backup supply on hand. So, if you're harvesting and reusing yeast and something just isn't right, you're not confident in that liquid culture that you have, that you've harvested, you can have a backup brick on the shelf ready to go in an emergency. So finally, it's easy to use, and we'll talk a little bit more about this later, but there's no specialized lab equipment or expertise required to use dry yeast. There's no need to be doing plating, cell counts, or have highly skilled lab techs in order to use dry yeast in your brewery. As I mentioned earlier, it can help facilitate planning. And also, we do have there's a wide range of different strains available for virtually all beer styles. Okay, now we're going to move into the shelf life study. So I'll discuss the protocol a little bit here. So the first part of our shelf life study is the forced aging test. And what this is simulated aging. By exposing fresh yeast to a specific temperature for a specific amount of time, we can simulate 1, 2, 3, 4 years of natural aging. So we did this for all of our yeasts, and then we look at, for fresh yeast and aged, the fermentative power and viability. And then for the aged yeast, the end of fermentation residual sugars, volatile compounds, acetaldehyde, esters, higher alcohols, and vicinal diketones. So Okay, so what's fermentative power? Fermentative power is a way that something we use to assess the vitality of the yeast. Viability is easy to measure directly, but vitality is many things. It's related to many things. So how do we want to be able to represent that numerically? So what we can do is we can take things that are easily measurable, like lag time, the rate of fermentation, which is ethanol produced per hour, and then the time to end of fermentation, and then build an equation that gives us a numerical results that can be an expression of fermentative power, and that can suggest to us the vitality of the yeast. So we'll talk more about vitality later. Okay, so forced aging tests for ales. Here we're looking at fermentative performance, the impact on rate and time of the fermentation. So here on the left, we have fermentation time, and then on the right, the fermentation rate, which is the ethanol production per day. And what we see for all the ale strains here, so on this lighter color, magenta or whatever this is the fresh yeast, and then this darker color is the 4 years forced age. And we look across the board and see virtually no difference in the total number of days to complete fermentation. And we also see virtually no difference in the amount or the rate of fermentation, the amount of ethanol produced per day. You see a little bit of difference here, but also mind the scale. This is a 0 to 4% alcohol per day range. So this is actually very, very small difference between those two results. Okay, now looking at volatile compound and ethanol production for all the different strains. So here on the far left, we have esters in parts per million, and then ethanol production. And then here on the right, we have higher alcohols in parts per million. And again, we see similar results, that there's really no difference in the performance in the fresh versus the 4 years forced aged yeast. Okay, this slide is a little difficult to see, but I'll try to walk you through it. So this is looking just at SAF SO4, and then 5 batches each of the fresh yeast versus the 4 years forced aged. And the blue dots represent the fresh, and the red are the forced aged. And at each one of these clusters, or each one of these dots, represents a sample. And you can see a little bit of variability at the beginning of the fermentation. But what you see as and don't really pay any attention to the lines that are on here, they're just kind of distracting. What you see as you move toward the end of fermentation is that these dots are all virtually on top of each other, and we're ending up with the same result at the same time in each situation. So the trials for this test here were 50 gram per hectoliter pitching rate in a standard wort, so all in the same wort, produced with a Weyermann syrup. It was a 15 Plato fermentation at 20 degrees C fermentation. Okay, so now the same tests for lagers, looking at volatile compounds and ethanol. So here in the upper left, you have ethanol production for S23, W3470, there's a typo there, and then S189, and then see very little difference in the ethanol production of those strains. Pay attention to the scales here as well. So this is 6.5 to 7.3. So this is virtually no difference in between these. Here on the right, we have the ester production and higher alcohols. And again, we're seeing the same thing here. There's virtually no difference between the fresh and the 4 years forced aged for the lagers. Okay, so we need to validate these forced aging tests, because it's not realistic. You know, no brewer is going to store their yeast in the same conditions that we did our forced aging test. You know, why would you do that? You're most likely going to be storing it in a cooler in ideal conditions. So so we need to do a natural aging test in order to validate those results of the forced aging tests. But another thing, actually going through with the natural aging test, what it allows us to do is to look at different storage conditions. So we can look at different storage temperatures and determine what the ideal conditions for storage are. So this set of trials is very similar. We start with fresh yeast, looking at fermentative power and viability, and then moving to the 44 months of real aging at 3 different temperatures: -20 C, which is -4 Fahrenheit, 41 Fahrenheit, and 77 Fahrenheit. And then again, look at fermentative power, viability, and then the end of fermentation, residual sugars, and volatile compounds. Okay, so here we're just looking at SO4, but we see the fresh batch here as the control, and then the 3 different storage conditions. And what we see is that, again, this is 15-degree Plato wort, a little bit different pitching rate here. This is 40 grams per hectoliter, and these are 50-liter fermentations. But what we see is that the fermentation kinetics are virtually the same. The lines are stacked on top of each other regardless of the storage condition after 4 years of aging. Here with 3470, we see a little bit different result. We're starting to see some effect on performance with the different storage conditions. So a much lower apparent degrees of fermentation with the yeast that was stored at 25 C. So that's 77 degrees Fahrenheit. Again, that's not a very realistic storage condition, but we do see that after 4 years has an effect on the performance. We can also see that yeast stored at 41 Fahrenheit and -4 were also somewhat affected, but to a lesser degree. But what can we conclude from all this? Well, what we conclude is that there's no significant differences between the fresh and the aged yeast. Actually, for the ale yeast, we saw that after 4 years, there was no significant differences. But for both ale and lager, we decided to use 3 years as our shelf life, erring on the side of caution. Also, you know, if you're storing your yeast beyond 3 years, I think there's something else going wrong. 3 years is a really long time to have yeast sitting around in storage. The other thing that we conclude is that storage at cool and dry conditions did for long periods. So, you know, the ideal condition was, it's around 4 degrees C or 38 to 40 Fahrenheit, somewhere around there. But what this also tells us is that for short periods of time, say during transportation, that we don't have to be worried about short-term exposure to temperature extremes during transportation. So, okay. Now we're going to move into the rehydration, viability, and vitality study. So the first thing I'm going to do is go over the procedures for rehydration, and then also the procedure for direct pitching on the next slide. So these have evolved a little bit over time, but these are the current recommended procedures from our tips and tricks documents. But for the rehydration temperature, we recommend between 10 and 28 degrees Celsius or 50 to 82.4 Fahrenheit. And what that should really be is really you should shoot for being near your fermentation temperature, whether you're doing an ale or a lager. So, sudden temperature extremes are really what you need to be cognizant of. So I guess what I really should do is start with the overall process. But the process of rehydrating is to add the dry yeast to 10 times its weight of water, let it rest for 15 minutes, and then stir gently, and then pitch into your fermenter. That's the basic process. 10 times the yeast weight in water. What does that mean? Well, for 500 grams of yeast, that would be 5 liters of water. But for working in pounds and gallons, 1 pound of yeast, you would need approximately 1.2 gallons of water for the rehydration. It's also important to add the yeast when you're adding it to the liquid, to add it slowly. You want to pour it at a steady rate, and as it hits the liquid surface, you'll see it spread out and disperse over the liquid surface. If you just dump the entire quantity into the liquid all at once, it'll plunge through the surface of the liquid, which will seal over it, and you'll create a lot of clumps. What one of our colleagues loves to say is that pretend that you're pouring a beer. You would never just turn your beer bottle upside down in your glass. So pour the yeast like you're pouring a beer. Okay, next is direct pitching. So as we've talked to brewers over the years, for a long time, rehydration was the only thing we recommended. But we talked to many brewers who just pitch directly into the fermenter. So we, part of this study is that we wanted to validate that that's okay. Is this potentially not the best scenario for the brewer? So we decided to do the study. But the procedure, essentially filling the tank cone during knockout with wort, at the temperature that you intend to ferment, whether it's an ale or lager, then sprinkle the yeast on the surface in the cone, and then complete filling the tank with wort. And that gentle agitation as you continue filling the tank will help incorporate the yeast into the liquid. For home brewing, or there may be other situations where it's not really possible to fill at the point that it's just the cone. It can also be pitched into a tank full volume as well. So how does the rehydration process impact yeast cell viability? So to answer this, we designed a study, and I'll go over the protocol here. But first, we rehydrate dried yeast in 10 times its weight of various media, and then check the viability at different points in time over a period of 45 minutes. So we check viability at 15, 25, 35, and then 45 minutes. And then each one of those, we have 3 different agitation treatments as well. The first is without agitation. So the yeast is poured on the liquid surface, and then we do nothing. It's the rehydration is just allowed to carry out on its own. The next condition is with moderate agitation. And this is where the yeast is placed on the liquid surface. We wait 15 minutes and then agitate at 100 RPM. So this would be the most similar to the recommended procedure we have on the previous slides. Finally, we have violent agitation. So yeast is placed in a sterile flask. So the dry yeast in the flask first, and then the hydration medium is poured on the yeast, and then a violent agitation is applied every 2 or 3 minutes. So during these trials, we also looked at a variety of rehydration temperatures, ranging from 8 Celsius all the way up to 40 Celsius, which equates to 46, 54, 61, 68, 90, and 104 degrees Fahrenheit. So we can see what effect rehydration temperature has on viability. But then we also looked at water versus wort. Many of you have probably heard, don't rehydrate yeast in distilled water, or don't rehydrate it in tap water. There are various myths out there. So we wanted to validate those. So we looked at 3 different types of water: distilled water, mineral, and tap water. And what tap water is it's actually Ghent, Belgium water, but it's a municipal water supply that would likely have some amount of chlorine or chloramine in the water supply. Then we looked at wort of 3 different densities, so 7-degree Plato, 15-degree Plato, and 25-degree Plato. And then finally, the viability tested after each of these conditions was measured using the trypan blue exclusion test. Okay, looking at the results. So first, for the ales, we look at the influence of temperature and agitation on viability following rehydration. So I have 3 different yeast strains here. And what these represent, I can't really fit all of the strains on one slide, but this is kind of a representative range of the more robust versus a more sensitive yeast. So T58 is very robust to rehydration, a little more sensitive, and then S33 would be kind of in the middle. And then we look at here, the different colors are the different agitation treatments. So blue without, red moderate agitation, and then the green. And the first thing that jumps out to me is that the violent agitation condition seems to be consistently having an effect in reducing the overall viability of the following rehydration. But for the no agitation condition, we have very high viability. And if you look at T58 here, as we move toward the warmer temperatures, actually with most of these, as we move toward the warmer temperatures, you kind of see a reduced effect of the different agitation methods on the viability. I would say the one exception here, US05 at 40 C, you see that it's decreased there, but I would also point out that this is kind of an unrealistic condition. This is at 104 degrees Fahrenheit here, and here back at 20 degrees C or 32, well, 20 degrees C is going to be a more realistic condition that you would be at. But what we conclude from all this is that in general, the best conditions are the warmer temperatures for the ales. Okay, here looking at lagers, again, looking at one that's, and I'm going to jump back just for a second. I do want to point out the scales that we have here too, because this is 50% viability to 100. So rather than doing 0 to 100 on the scale, this will kind of exaggerate the differences here. So it's actually a very, very small amounts of differences between these samples. Okay, now looking at the lagers. So here again, we're seeing that the violent agitation is affecting the viability. And for the lagers, we're actually seeing the higher viabilities here, you know, kind of at the cooler temperatures within typical lager range. And again, seeing a little bit of that reduced effect of the agitation method. But we can conclude here that the best conditions are either without agitation or moderate agitation. Okay, moving on, looking at the influence of rehydration time on viability. So here we have ales on the left, lagers on the right, and then viability here, again, the scale 60 to 100 here. Looking at T58, USO5, and SO3 at the four different times of rehydration. And what you can see is looking just at T58 across the board, regardless of the amount of time allowed, you see the same viability for each. The same for USO5 and SO4, that the amount of time allowed really makes no difference. Seeing the same thing over here for lagers for S23 and S189. So what we can conclude here, oh, and I should say that for these tests here, these are all using the second best condition. So that's the moderate agitation at 32C. So what we conclude is that rehydration is complete after 15 minutes with excellent viability. Okay, now moving on to the influence of the rehydration medium, specifically in this slide, the water quality on viability. So we have ales and lagers both on one chart here, again using moderate agitation at 32C. Yeast in these conditions was rehydrated in water, tap water, mineral water, and distilled water. So in blue here, well, actually, let's just look at T58. You see virtually no difference in the viability, regardless of the type of water, same as S23, and the same as USO5. So clearly, water quality does not significantly influence viability during rehydration. And then for all the conditions that we tested, the overall variation in viability was ranged from 75 to maximum for all the conditions that were tested. Okay, now still looking at the influence of rehydration medium, but now looking at sugar and temperature on viability. Again, ales and lagers on each slide. So T58, S23, and USO5. But here we have two different temperatures. So we have 20 degrees Celsius and 7 degrees Celsius. And we have, in this light blue, we have water as the control. I believe this was an average of the results of the previous slides. And then we have wort at 7 Plato, 15 Plato, and 25 Plato. And what you can kind of see, even though the difference in the viability is extremely small, we actually surprisingly see a little bit of an increase with the higher sugar concentration within the wort in pretty much all of these situations with all the strains. So what we can conclude is that the sugar concentration does not really significantly influence viability when you're rehydrating dry yeast. And also, surprisingly, I think a lot of us might have expected that once we got to 25 degree Plato, that there would be some osmotic effect and that the yeast might suffer from rehydrating in that. But The data clearly doesn't show that. Okay, so now we're moving on to a little bit of how to use ADY and whether you should rehydrate your yeast or direct pitch. So how does direct pitching influence yeast cell vitality? So again, we conducted some tests, and I'll go over the protocol here. So for the ales, we again took the kind of the representative strains, the most sensitive, kind of medium, and the most robust of the strains. Same for lagers. And then looked at 3 different rehydration conditions. The first was water at 30 degrees C, moderate agitation. So that one, we used the symbol W for that. Then looking at 15-degree Plato wort at 30 C with moderate agitation. And we use the 15P as the label for that. And then finally using no rehydration. This is just direct pitching into the whatever the vessel the fermentation was conducted in. Each wort for both ales and lagers was at 15 Plato, standard wort. For ale, pitching rate of 50 gram per hectoliter, 100 gram per hectoliter for the lager. And then for ales, fermentation at 20 C, 14 C for the lagers. Okay. And then the forced aging test that I discussed earlier will kind of play into this study as well, because when we look at all of these different conditions, we're also going to test all of these conditions for both fresh dry yeast as well as 3-year forced aged yeast. So again, some more of the protocol or the final analysis that we conduct after these trials. We're going to do tests of fermentation performance in triplicate, and then we're evaluating fermentation performance by measuring the weight decrease of the medium, and then making a correlation of that to the sugar conversion into CO2 and ethanol. We're also doing an analysis by HPLC of ethanol production as well as volatile compounds, looking specifically at acetaldehyde, esters, higher alcohols, and VDK. All right, let's take a look at the results. So first here, we're looking at US05. Again, in the upper right here is just a reminder of what the labels mean underneath the charts of the 3 different conditions. So direct pitch, rehydrated in water, and then rehydrated in wort. On the upper left, you see the fermentation kinetics. Depending on your screen size, it may be hard to tell, but there are actually 3 lines there pretty much laying on top of each other. The fermentation kinetics of each of the conditions is the same. Apparent degrees of fermentation, achieving the same results here, consuming the same amount of sugars. On the upper right, you see the ethanol production. This is a very narrow scale. This is from 6 to 7. So this full chart is only a range of 1% ethanol. So virtually no difference in between the results here. It might be equivalent to the results you would see between any fermentation. Here on the lower right might be interesting. Here in blue, we're looking at VDKs. In gray are esters. The darker orange or higher alcohols, and then the yellow is acetaldehyde. And you may be thinking to yourself, well, that's over 250, 275 part per million VDK. That's or part per billion VDK. That's extremely high. Well, this it's not really the point of the data here. So when they took the measurements, they took it at the point where there were 2 consecutive days of the same gravity. So there had never been an opportunity for a VDK rest. So 2 degrees or 2 days in a row, the same gravity, it's declared end of fermentation, and they run the tests. So what's really important is that across the board with the different conditions, you see that we're getting the same result, regardless for esters, acetaldehyde, VDK. Okay, same thing, looking at another strain, S23, but it's basically a repeat of the previous slide. The kinetics are the same, degrees of fermentation are the same, ethanol production, and then again, the volatile compounds for each condition, you're seeing the same results across the board. Okay, another ale strain, K97, and again, seeing the same thing. Kinetics are the same, and then volatile compounds across the board, everything producing the same results regardless of whether it's direct pitching, rehydrated in water, or rehydrated in wort. Okay, and then we look at back to US05, comparing the kinetics of the fresh ADY versus the 3-year forced aged, and then compare the fermentation kinetics, so the ethanol over time, and you see that for regardless of fresh versus aged and the condition, see virtually the same fermentation kinetics. So performance is not affected here. Moving to a lager. Here we have S23. So again, direct pitch, rehydrate in water, and then rehydrate in wort. Again, the same kinetics, apparent degrees of fermentation. This is a very narrow range, 78 to 84, so virtually no difference. And then here on the right, again, VDK, higher alcohols, volatile compounds are all the same regardless of rehydration or direct pitch. Okay, then looking at fresh versus aged S23, and we see the same thing we saw with US05, that the kinetics of the fermentation are virtually the same for regardless of direct pitch or rehydrated in water wort, or whether it's fresh versus aged. Okay, and then so what do we conclude on all this? How does rehydration impact viability? First, these are all the things that we looked at. Agitation, the method of agitation has the greatest impact on the overall rehydration process. We saw that violent agitation can reduce the viability. So because of that, we recommend very gentle, moderate agitation, waiting that 15 minutes for rehydration, or using no agitation at all, direct pitching. We saw that temperature had no significant impact when using no or moderate agitation. We did see some influence of temperature in relation to the agitation method, but no difference really when at no or moderate. The type of media tested had no significant influence on viability. You can use wort of various gravities or whatever water source you want to use, providing it's a sterile water. Rehydration time had probably the least amount of impact. So there was no observed impact on rehydration at the times we looked at. Rehydration is complete after 15 minutes. And then final conclusion for ales and lagers is that we see the consistent results between ales and lagers. Okay. So how does direct pitching impact yeast cell vitality? Direct pitching, we saw from the data that there was really no impact on fermentation kinetics, ethanol production, attenuation, or volatile compound production, even when the yeast had been 3-year forced aged. So yeah, it's okay to direct pitch. So now, because of this study, this is what we say. We say, take it easy. And this easy to use logo, you will see it on products, any of our products that have been validated through this process. So there's several criteria that the yeast must meet. There are a couple brewing yeasts that will not get this easy to use designation or certification yet. Right now, that's HA18 and DA16. And that's because those two particular strains have an ingredient that is powdery and has potential to create a little bit of dust. So that's actually one of the criteria that we look at. But virtually all of our other brewing yeasts, if you see this, means that it's okay to direct pitch. So. Okay, I'd like to acknowledge some of our partners for doing the R&D you saw in this presentation. The first is the Maurice Institute. We work with the Maurice Institute often for R&D projects. And I believe Laurence van Nederveld was the lead on this project, working with the Fermentis technical team. So I'd like to say thank you to the Maurice Institute and the Fermentis technical team for all the hard work, conducting the trials and putting the data together for us. Okay, the next thing I want to point out is we have some upcoming webinars. We kind of held off communicating them because we were finalizing some of the details, but we have a cycle of 4 webinars coming up in the very near future. The first beginning June 23rd, but they're kind of complementary webinars. So the first one we call the first dimension, the baseline, and this is where we will look at intrinsic characteristics of the yeast. And then the next webinar will be called the second dimension. And this is where we'll look at how yeast strains all respond in their own unique ways to differences in fermentation parameters like pitching rate, fermentation temperature, and wort density or original gravity. So these seminars are all about 1 week apart, same time and place that we're meeting today. So webinar 3 is called the third dimension, but this will start looking at yeast interaction with raw materials, aka starting to discuss the all famous or all popular word these days, biotransformation. But we'll be looking at a couple different studies, one that looked at ideal strains for New England IPA, but also a really cool study looking at single hop interactions with various yeast strains. So the first one will be looking at virtually all of our yeast strains and their interaction with cascade hops. And then finally, another popular topic these days, we'll look at the last frontier and discuss production of hard seltzers. So that'll be July 14th. So stay tuned. I don't have a link right now here, but you all receive a PDF of this presentation, so you'll at least know what the topics are, but we'll be announcing these on our social media. If you received an email invite for this webinar today, you'll likely also receive an invitation announcing these as well, but it'll also be on our social media. So stay tuned. More information on those is coming. So thank you for your attention. Right now, we'll move to taking some questions. And I think maybe Ann and Jose might join me for that. But yeah, let me know what questions we have.
Awesome. Well, thank you, Brian, for that excellent presentation. There were not a lot of questions during the presentation. Yes, actually, two. I'm going to put the chat in full screen, like that we can follow up a little bit if there are questions. So one of them was about the batch size of all the trials you showed. If there were only lab trials, pilot trials, brewery trials.
There's a variety. So a lot of the trials that we do, it kind of depends. So we can do, I think all the ones in this were anywhere from 250 milliliter to 50 liter trials. But we, in our R&D department, I believe they can do anything from 50 milliliter automated trials to robots that conduct large quantities of 250 milliliter fermentations that are monitored in real time. And then we can also do in the lab in a 5 liter fermentation that's monitored for the full time.
Awesome. Yes, I was commenting on the chat as well that one thing is the lab trials we do, another thing is the pilot trials we do, and also third, but not least and very important, is all the feedback we get from customers around the world that me, you, and Anne deal with them on used to be quite more often than now, but and pretty much they see the same results that we see in our trials, but on their daily brewing.
Mm-hmm.
So I'm going to move to the next question, Brian. It's a question from Stephen Bartel. So he's asking, do you recommend the same pitching rate for all words, or does it scale with gravity?
Good question. So in general, I would say, one, it's up to the brewer, but two, we have a recommended range. And in general, yes, I would say to shift toward the higher end of that range as you shift toward a higher Plato wort. However, it's really different depending on yeast strain as well as the flavors that you want to develop in the beer. So Fermentis's take is to recommend a range that we know will produce a successful fermentation, and the brewer through his creativity and through his experience and his own tasting can adjust and adapt that pitching rate range. For ales, the pitching rate is recommended 50 to 80 grams per hectoliter. But that is just a guideline. There may be situations where you want to go above or below that, depending on the beer style or the strain. And then again, for lagers, we recommend 80 to 120 grams per hectoliter. But again, if you're starting within that range, you're kind of in the safe zone. But then, that's something for you to conduct your own trials and fine tune that.
Mm-hmm. Excellent. Brian, if you want to give some rest to your voice, I can take the next question. And I will expand a little bit on what you were saying. Actually, we are realizing that yeast, it's kind of like a boat that you need to steer. So some strains, will produce different aromas and flavor depending on fermentation temperature, pitch rate, and so on. And others, like no matter the fermentation parameters, will output the same beer. So as Brian said, we give guidelines, but then, and if you keep following these webinar cycles, you will see that we have a lot of data to really steer and fine tune what you can do with some of our strains. Also, Dustin was asking what are the 2 strains that you so far will recommend to rehydrate instead of direct pitching. I put on the chat that actually those are 2 fermenting solutions. We have the A16 and HA18. And as Brian mentioned, they are a mix of yeast and enzyme. Enzyme so far being in a powdery form, it can produce a dust cloud that you can inhale. So that's why we recommend to rehydrate those fermenting solution prior pitching. Is just for a health concern more than a practical point of view. And I'm reading on the chat, Philip is asking us, how does osmotic pressure of direct pitching toward without rehydrating not affect the cells negatively? So that's a really good question. And actually, it affects the yeast membrane. And back in the days, in the 90s, when we first released dry yeast to the market, we were not as good as today into drying the yeast. So that will affect the membrane. And that's why also, if you were direct pitching into a high concentration media, you will have a membrane that will not resist that osmotic shock. But today, because we are able to dry the yeast without affecting the membranes can resist that kind of treatment, which actually it's a shock for sure. I see someone typing, Emin is typing in a language that I cannot read, I'm sorry. If you can type in English or French or Spanish. I think, Anne, do you speak German? We cannot hear you, Anne, by the way. Okay, Philip, well, thank you. That the explanation was clear. We have some time, guys, so please feel free to ask us anything about this presentation and also other questions you may have. We will try to not spoil future webinars where we will keep talking a lot about yeast.
Well, I either covered it well or I went way too fast and there's no questions.
It's no, you covered very well. Well, this is a good question, actually. Do you want to take the one from Tyler, Brian?
What is the amount of service?
Or, I mean, we can talk about why.
Perhaps I don't understand the question.
So how does amount of surface area part play into pitching? Yeah, Tyler, can you develop a little bit your questions? Okay.
The surface area on the top of the liquid surface?
I think we can talk about that, and we can talk also about why the yeast has a granulate form, because it goes into that direction too.
Yeah, I think I understand the question there. I think he's talking about, maybe how broad a vessel is and how, maybe you've only filled a small part of the cone, so the liquid surface isn't as broad. I would say that there's, you definitely need to be, as you're filling the cone, past that 10 times its weight of liquid. But also, we haven't done any specific work on it, but I would say it's safe to assume that, the broader the surface, the more space you have for the yeast to spread out over the surface. So I would say that, a broader, waiting till you're at the top of the cone or having a broader surface would be advantageous, but we haven't done any specific work on that I know of.
Yeah, excellent, good answer. So someone is asking if we are working on a Kevai quiet yeast. So just so you know, we're working on a lot of different things. We used to kind of give some scoop about what was coming next to the market, but at this point, and with all like the pandemic going on, and we prefer, many things have been delayed due to circumstances. So I would say please stay tuned and you will see. But we're trying to put new things on the market every year.
Yep, there's a lot of things in the works, but some of them have been delayed because of current situations across the globe. So.
It's interesting to see how attendees are typing questions and you don't know what is going to be. I like the unexpected.
Yeah,
do you want to answer that one?
I might be able to try that a little bit. So the question is from Steve is, have there been any studies regarding glucosidase production of our strains? So there are some suppliers out there that have done some work on that, and Fermentis's take is a little bit different. We're not measuring beta-glucosidase activity of the strains directly. However, we're conducting studies that suggest that there might be something happening there, or at least there's evidence that supports whether a strain may be exhibiting beta-glucosidase activity. But what Fermentis does is we try to focus on the flavor impact of the final beer. Does it really matter that it's a result of the beta-glucosidase activity, or does it matter that the flavor or the aroma you wanted in that beer comes through in sensory? So we do look at some analytical conduct fermentations and then look at analytics as far as total hop oils that end up in the final beer and various hop volatile compounds. We are measuring those things, but then also doing sensory to complement those things, because what really matters is if that flavor ends up in the final product.
Mm-hmm. Actually, yes, to add on.
So.
Can you hear me?
To add on what you were saying, yes, now we can hear you, Anne. Excellent.
I wanted to add something for the wine strain. I think there was a question. For sure. Also in our wine strain portfolio, we also look at this type of activity, and we measure it, but we also mainly look at the sensory profile of the wine more than anything.
Yep. Excellent. Yes, I will add on what Brian and Anne said, that there is a couple of papers out there, and when you look at strains and their beta-glucosidase activity, you will realize that most of Saccharomyces cerevisiae don't have a high activity. Actually, Brettanomyces, it's the yeast that have a lot of beta-glucosidase activity, but it's not something that you will use to make, for example, a New England IPA. So at the end of the day, we're looking what's the impact of that strain with the hops you use into the aromas creating into the beer.
Yep. Also, POF, even if they're not Brettanomyces, POF positive strains tend to be higher beta-glucosidase activity as well. At least that's what I have read. But the POF character, which is the spicy clove phenol type of character, actually has a tendency to mute hop aromas and flavors. So it's kind of a contradictory effect there.
Mm-hmm. And do you want to answer to Trevor Christie? There is a question.
Did we push the study past 3 years? Are we talking about the shelf life study here?
Yeah, so
I guess so, yes.
I'm assuming.
Yep.
I believe the more we did was 4 years, but that's to my knowledge. I have never seen number past 4 years.
Right.
Mm-hmm.
As far as I know, we went to 4, but then we decided to just make the shelf life 3 years.
Mm-hmm. It's yeah, I will add on that, Trevor, that with dry yeast, through the time you are losing viability very slowly because the yeast is dry and also it's in a vacuum packaging or nitrogen flush packaging for the home brewers, sachets. So through the time, the yeast is slowly dying, but dying. In my experience, I deal with a lot of home brewers, and some people will say, hey, I found a Fermentis sachet that expired 5 years ago. Can I use it? And the answer would be like, well, if you want to use it, go for it. The thing is that I don't know what's the viability left into that, but for sure there will be some dry yeast alive, and most of the time people will do a starter, and then that's it, they're ready to go. So the results we show in the study is because between fresh dry yeast and dry yeast up to the age of 3 years, the product still into the specifications we have in our technical data sheet. So that's why we show that study, because you don't need to get the freshest yeast possible. It's into the BBE date. It's perfect to use. It's yeah, Dustin. Thank you for the privacy. I'm going to put my chat on the email. Sorry, I'm going to put my email on the chat, and please shoot me an email.
Oh, you're welcome.
Welcome.
I see an old friend typing. Here comes a hard one.
Oh, so it's for you, Brian. You take care of that one.
Suspense.
Suspense.
Yeah, I think we'll just take a couple more, I would say.
Mm-hmm.
Okay, yeah, that's a good question. And I really probably should have covered that during the rehydration procedures. But the question relates to using partial sachets. Our official position is to not reseal sachets. However, we know that it's done on occasion and that brewers have had success doing that. If you make the choice to do that, the best practice would be, I mean, if you can be very, very sanitary doing it, I think the best practice would be vacuum sealing. But what some other brewers do is just kind of very carefully fold the sachet closed, pressing out all the yeast, or all the air, and then taping it closed. But this question relates to soft sachets as well. Sachets, when you receive them, should be firm, and if you have one that is very soft, you should not use that. And the reason is, just like with an open sachet, is that air and moisture that is in the air is detrimental to the yeast. So when you open that sachet and it's exposed to air and moisture, that begins to just a little bit rehydrate the yeast, and it begins to activate the cell metabolism. And then if there's no carbohydrate source for the yeast to consume, then it can begin to autolyze and decrease in viability. So if you're resealing sachets, we really can't offer the guarantee that we typically offer with our product. Can't really guarantee it at that point. Also recommend not using soft sachets. Just contact your supplier, and they should be able to offer you a replacement at no cost.
Mm-hmm. Yeah, at the end of the day, we don't know at what rate the viability is going down in an open sachet in your brewery, depending on temperature, moisture, and all that.
Something for sure to avoid once you have an open sachet, and if you put it in a fridge and you get rid as much air as possible, is to not take it in and out the fridge.
Right.
Because every time you have a change in temperature, you have condensation. That's going to increase the humidity, and that's really going to affect the viability. So
right.
Only do it once.
Yep. And another thing I guess I didn't talk about is that when you do have that condensation, you know, if you've taken it out of a cooler and it's warm and humid in your brewery, there can be quite a lot of condensation. And those droplets on the sachet can actually be a way to introduce a contaminant as well. So I would just be cognizant of that. And if you do reseal a sachet, use it within like 5 days. Don't wait much longer than that.
I think we can take 2 more questions and we can call it a day, call it an evening.
Cool.
But we have 3 people typing, so maybe we'll have to choose.
So Trevor's question here about ideal storage. So the ideal temperature in our studies was 4 degrees. Is that right? Now I'm confused. It's about 38 to 40 Fahrenheit was the ideal in our study. Again, you know, frozen was okay as well, but you know, less optimal than just storing cool. But we didn't do, as far as I know, we didn't do a range of temperatures between what we say is ideal, that, you know, 38 to 40 all the way down to freezing. So I would say right now the ideal, just consider it to be around 40 degrees Fahrenheit. And I guess that's question on ideal temperature. Maybe I didn't emphasize it back when I was on those slides, but you know, a lot of the 3-year shelf life is based on ambient storage. So, you know, you actually have far better results by storing cool. So.
Yeah, usually cold temperatures keep things shelf life longer. And as Brian mentioned, there is no free water. So if you want to keep them like in the freezer and you have space in your freezer, why not? It's your call.
Yeah.
All right. I think that's it. Thank you everyone for attending the webinar. Cool. And please stay tuned for the next sessions to come. Registration will be the same way to register for this one. So looking forward to have you all on the next webinar. Thank you. Bye.
Thank you all for coming.
Thank you.
Bye-bye.